Here we are, the end of the lecture series in computational electromagnetics. So right now, you are all experts in computational electromagnetics. And we're at the point now where we want to design something. Not only design it, but we want to optimize it so that it works as good as it possibly can. And so that problem is optimization. How do we test all these different parameters of a device design in an intelligent and efficient way so that we get a really, really good working design? And so an element within this is the model of how we simulate the device. So right now you're experts in that. So what we want to do is wrap a shell around that, and how do we iterate different design parameters to come away with the best design. So I'll introduce optimization and really try to describe the problem it is we're up against. And then we can roughly divide the optimization methods into the two categories, the direct methods and then the stochastic methods. The direct methods, we somehow jump straight to the optimal design, and in stochastic optimization, we realize that it's probably a little bit more difficult than that, and we want to incorporate some kind of randomness into this to more efficiently search over a larger solution space. And then I'll end by describing one trick we use a lot in calculating our merit functions that I call the rectangle algorithm, and that'll make sense when we get to it. So first, what is optimization? Well, let's say we have a diffraction grating, and what we want to do is prevent any diffraction into the zero order transmitted mode. So we have an incoming wave, and it diffracts into potentially a bunch of different directions, and we have a zero order mode. We want all of the power to go into those higher order modes and not the zero order mode. And we want to do that just by adjusting the depth of the grating and the duty cycle of the grating. So D and F. Everything else, for some reason or another, is fixed. So we come up with a range of F's and a range of D's. So this entire space we call the solution space. Our answer lies somewhere in this plane. So for example, if we pick this point, which has both a small f and small d, we see we have a little tiny bump on top of the substrate. Way over here, where we have a large f and large d, our device looks a little bit differently. So each point in this solution space refers to a specific device design. So what we need to do is search that entire space and figure out the best design. Now, this only has two parameters. This is probably a quick simulation. The reality is that we're doing optimization. To fill in our entire solution space may take centuries, and we are looking for a more efficient way to do that. So if we were to fill in that specific solution space, in fact, this is what it looks like. That is an ugly, ugly solution space. It's full of lots of peaks and valleys. And here we're plotting the diffraction efficiency into that zero order transmitted mode. We want to minimize that, so we're looking for zeros. We're looking for these dark blue regions, and we see several of them. Which one's better? And how do we get to whichever one's best? So that's optimization. And if I were to plot this more as a surface plot, it looks even uglier. So it's a very, very ugly mountain range kind of thing. So we have a difficult task of finding the best point in this. So we have regions where we have local pockets of zeros, or close to zeros. And we would call these local best solutions. So if we have an optimization algorithm, for example, that just goes downward in slope that would converge to a local best solution, that may not search the entire solution space to find the best. So how is it we search the entire solution space and don't get stuck? And these are all the tricks that go into optimization algorithms to try to search as much of space as we can, as efficiently as we can, without getting stuck in local bests. I'll also mention that if you are using some kind of random optimization, that's probably because you don't know very much about your solution space. And it is almost always impossible when you run your optimization and you get an answer that works good enough, it is almost always impossible to say that is the global best. In order for you to say something like that, you have to know something about your device, the design, and the solution space. And chances are, if you know that, you probably don't need to do some kind of random optimization. So I would say it's actually impossible to say that you have converged to a global best solution. However, if you're an engineer and not a scientist, as long as your solution is good enough, we're done. So we need something that is called a merit function, sometimes called a fitness function, but it is a single number that tells us how good our design is. In this case, it's easy. It's the diffraction efficiency into that zero order transmitted mode. Other times it's more difficult because there might be other things we want to consider. Maybe we not only want to consider diffraction efficiency, but we want to consider the bandwidth. Maybe something about polarization, maybe the size of the device. Maybe we could get that diffraction efficiency with some extreme value of D or F, but we want to avoid those extreme values. So there may be multiple considerations, and it becomes very difficult sometimes to come up with a single number that tells you how good the design is. So here, we've revised our merit function actually to take into account bandwidth. We not only want a low diffraction efficiency, maybe we want broad bandwidth. And so we need to consider these together. So for example, while the best or the smallest number might exist right here, we also see it exists over a very narrow range of F and D, and that may not be physically realizable because maybe we can't manufacture a device to those kind of tolerances. Whereas over here, we see over a greater span of F and D, we can get a pretty good zero. Maybe that is a better solution, and we would not have converged to that if we did not consider the bandwidth, if you will, of F and D, or the structural tolerance of the device. So always keep rethinking the merit function. Build in reality into it as much as possible. Keep rethinking it. We not only want to consider all these things that are important, they may not be of equal importance. For example, diffraction efficiency might be more important than bandwidth. So how can we suppress the importance of bandwidth or enhance the importance of diffraction efficiency? How do we do all that? Well, one thing we can't do, we can't multiply by a scalar constant. Let's say bandwidth, in our case, is the most important. So we're going to multiply bandwidth by some alpha. Maybe this is a factor of 10. Well, this alpha can be factored to outside of our merit function. So what we see is we have our original diffraction efficiency times bandwidth, our original merit function, just scaled by this constant. And this constant really could be associated with either one of the two, and it doesn't matter. It doesn't change things. So multiplying by a scalar constant isn't good enough. So what are some better scaling techniques? I like to take natural logs sometimes to suppress the importance of certain metrics. Sometimes I'll raise them to some kind of exponent if I want to enhance them. Now another thing that's very important is we have to consider these individual metrics, diffraction efficiency, bandwidth. Are they less than 1 or greater than 1? If they're greater than 1, squaring it will make it bigger and enhance it. If it's less than 1, squaring it, in fact, will make it smaller and suppress it. So we need to think about the magnitude of the numbers that we're taking the logs of or taking exponentials. Take that into consideration so that you know whether you're enhancing it or suppressing it. But essentially, the merit functions I typically use are a series of products where I multiply together everything that is important to the design, and I scale them with logs or exponents to try to convey relative importance. But they all tend to take the form of a product series. Here are what I think are the most common optimization algorithms, and I have them divided into two groups. One is direct methods, where there's nothing random about it. We just somehow jump in and go straight to a best solution. Then there's the stochastic optimizations with built-in randomness, which tend to have a much better ability to search the entire solution space, whereas the direct methods will focus in immediately on a local best. Except for the complete search, which I put under a direct method. This usually is not a practical thing to do. So this means you search every possible combination of everything in your solution space, you calculate that merit function or fitness function, and you find the very best one. That is the only way that you can really guarantee that you have a global best, unless you know something about your device or solution space. So other than the complete search, which is a little bit of an anomaly, we have a variety of different methods, but probably the best and simplest and most common is just gradient descent. So we look at the slope of that fitness function in the solution space, and we either go uphill or downhill to get to a minimum or maximum, depending how you're optimizing. So it's very quick. It gets to that local best very quickly and very rapidly. However, the gradient descent does not do this global search. It just locks onto very rapidly a local best. So what tends to be a good idea is you'll do your random stochastic optimization, and when it begins to converge, you can then jump over to a gradient descent to more rapidly converge to that local best. On to the stochastic optimizations. This, we are somehow randomly choosing designs throughout the solution space, hopefully involving a little bit of intelligence so we can do this more efficiently and more rapidly. Within that category of optimization, we have particle swarm optimization, which is relatively new, genetic algorithms, which are very old, very mature, and then a related simulated annealing. So simulated annealing is a stochastic optimization. It's involving randomness. However, it takes on more properties of like gradient descent. So maybe even locally, your solution space looks rough and confusing. Simulated annealing can help you lock on to that local best, but also avoid a rough or ugly looking solution space. So, global best. This means somehow we have thoroughly searched every possible solution and found the absolute very best one. And it's absolutely impossible to say that you have found the global best solution unless you know something about the problem or you've done an exhaustive search, a complete search. So if you know, for example, that you have a smooth solution space, well, you can lock on either to a minimum or maximum and then say, with a pretty good degree of confidence, that's the global best. However, you had to know that your solution space looked like that. More realistic solution spaces look like what I've shown a few slides ago, where you have all these humps and valleys and it looks like a very rough mountain terrain, in which case we can't make those same conclusions. Before we go into some specific optimization algorithms, I want to summarize a few points I know I've made before, at least most of these here. If we know almost nothing about our device, this is where the stochastic or the random optimizations are king. They can very efficiently, very effectively search the overall solution space and determine a good solution. Now that we have no guarantee that's the global best, but if we were engineers and not scientists, we don't need the absolute best. We just need something that works good enough. And that's usually what comes out of an optimization like this. Only an exhaustive search can really guarantee you have the global best. So comparing direct to stochastic, the direct methods they converge on a local best much more rapidly, much more efficiently. However, it is the local best, the best solution closest to where you start your search. So they're fast, but they don't seek out the entire solution space. So they're best for refining a solution that's already pretty close to being optimal. And then the last thing I want to mention, which we haven't discussed yet, is talking with people that do optimization. Everybody talks about the different algorithms, what's faster, what's more efficient. In my experience, all the algorithms work. It comes down to that fitness function or merit function. I might spend 2 months optimizing a design, and I will spend 2 days developing the algorithm, and the rest of the time playing around with the merit function. And watching it get stuck in local minimums or solutions that I know intuitively are not the best, and then I got to go back and tweak the merit function to weight the different considerations that I'm doing. And so I spend most of the time on the merit function. So to me, if you're sitting down at a table with a bunch of people that do optimizations, the discussion should be on how to construct these merit functions, because that is not straightforward, that is not easy, and I could say I spent orders of magnitude more time on that than the actual algorithms. Our first specific method, complete search, which is barely a method. We just set up a big loop that loops over all possible combinations in the solution space, calculate the fitness function, and see what happens. So doing a complete search, going back to this example of our diffraction grading where we want to minimize diffraction into the zero order mode, this is what our solution space looks like. And it's pretty ugly. And in fact, the global minimum, the absolute minimum, is sitting right here. But reality is, each one of these simulations, I've easily had simulations where calculating the fitness function at one frequency point for one device can take upwards of a day. So imagine we had to fill this entire plot here, where each pixel in that plot takes 1 day to calculate. That's just 2 design variables. We routinely optimize things that have dozens of design variables. So literally, it's going to take millennia for us to do complete searches, and it's just not practical. We can't do that. Gradient descent. So imagine our solution space looks something like this, and clearly our best solution will be right here, and we start our search out here. So what we do is we essentially go to all the design parameters and calculate the fitness function, wiggling each one of those parameters, and we calculate the gradient from all of that. Given the gradient, we know how to change each one of those parameters. So we do that. We change each one of those parameters, and we end up a little bit closer to the global best. And we're always, since we're walking down the gradient, we're always moving normal to these surfaces, and gradually we walk toward the global best and we find it. So again, this is not doing a global search of our solution space. It is locking onto the closest local best solution. So how do we implement this? Well, step 1, we define our starting point. So we come up with our position in solution space. And this is also not something we've talked a lot about. These different parameters could mean different things: fill fraction, grading depth, etc., etc. What I tend to like to do is normalize all those parameters so they go from 0 to 1. So this outer optimization algorithm is just working with numbers between 0 and 1. And then when I call my merit function calculator, the first thing I'll do in there is take all those numbers that go from 0 to 1, and I'll convert those over to numbers that actually make sense to the device, like duty cycle, grading depth, grading period, and stuff like that. But we start off with a starting point, with some position in our solution space. These are our design parameters that tell us everything we need to know about our design in order to calculate how good it works. Well, the next thing we do is we take each one of these parameters and we change it slightly, and we calculate how this fitness function or merit function changes. And depending what direction we move it and whether the merit function gets better or worse, we know which way we would move that variable to improve the design. So essentially we do that with all the parameters, and we don't actually update the parameter before we go to the next one. We keep all the original values, but we test each one of these individually. And in the end, we have the gradient. What we've done is we're calculating the derivative with respect to each one of these variables. So we do that. We calculate the derivative with respect to each one of the design variables, and then we update them all. And we only let it go some distance, and we'll control that through this parameter alpha. So we don't move the entire, our slope can potentially predict how far away that global best is, but we don't let it go that far. We make it smaller, like we give it a number by like 0.1. And we only move along that gradient by a distance of 0.1 normalized in some way. And we keep repeating that, and slowly we'll step towards the global best. And normally a dozen iterations or so, we're there. Whereas the stochastic optimizations, they might take millions of iterations, definitely at least thousands. Some final notes on the gradient descent. It's a first order optimization method. It really does not try to guess how far away that global best and go straight to it. It just does little tiny steps moving up or down the gradient. It always converges to the local minimum. It does not search the entire solution space. So it sort of locks onto or refines a design that's already pretty good. So we tend to only use it when we have a good initial guess. It's a really simple method. It takes you 10 minutes to implement something like this. It does converge slower than other direct methods, things like the Newton method, which actually try to predict how far away you are from a certain point to the global best. The problem with that is those types of algorithms can go unstable if you overshoot the global best. A lot of them get confused and they start oscillating back and forth. So I have found the gradient descent to be the most robust. And this also requires that the solution space is differentiable, which we can do numerically or analytically. Our next optimization algorithm will be genetic algorithms. This is probably the oldest and most mature of the stochastic type of optimizations. And there's all kinds of software out there. There's toolboxes for MATLAB and other software packages. So it's a pretty proven technique. And of course, it's based on biology and evolution. And if we think about biology, we all have our DNA, we have chromosomes, which are like little lines of computer code in our cells. And each one of these little bits defines something about us. So just like in our previous optimization, we had this string of numbers that defined what our design looked like. We call each one of those a chromosome, and this array of chromosomes we will call our DNA. And so we probably start off the simplest algorithm with two parents that each have their own DNA, and we would mix them in some combination and produce an array of children. Then we would simulate each one of those children, calculate the fitness or merit function with each one of those, and then we might do something like pick the two best children. And then those become the parents of the next generation, and we mix those children and we keep going. But there's all kinds of other things we can do. We can have illegitimate children where sort of a third parent comes in and introduces new randomness to the mix. Otherwise, your children all end up looking the same after some number of iterations. That's the basic algorithm. Parents breed children, we simulate those, we figure out the two best children, they become the next parents, and you can even have more than two parents. It doesn't need to parallel biology exactly, and we can mix any number of parents, one parent, 2, 3, 4, whatever. So here's the basic algorithm. We initialize our nth generation, so this will be our first generation. Then, so that's our set of children, and maybe we have 20 children. We simulate each one of these and calculate our merit function or fitness function for each one of those. Well, if suddenly those fitness functions, they exceeded our threshold and we have a design now that's good enough, well, we can choose to stop. If we don't, we go over to the reproduction step. This is where you choose your parents and you mix them in some way, so you do your crossover. Maybe there's a third parent, or maybe you somehow, in some other way, introduce mutations. So these are completely new chromosomes that don't come from either one of the parents. And then from all this, you produce your next generation of children. These are just designs at this point. And we simulate all of them, calculate their fitness function, and maybe now we have a design that's good enough and we'll stop. If not, this process just keeps going. And it's modeled after biology, so picture how organisms evolve over time, and this is how that algorithm works. Some final notes on genetic algorithms. This was inspired by natural evolution, and I can probably say that these are the most popular of the stochastic optimization algorithms. I don't know if it's the best. I'm not going to make any statements about what is the best. I can tell you times that I would use these versus particle swarm or something like that. I tend to use genetic algorithms when the chromosomes are very binary. It's either a yes or a no. If the variables are more continuously varying between 0 and 1, I would tend to prefer particle swarm optimization at that point. But both algorithms can do both things, so you're not limited. I just tend to lean towards GAs for binary type chromosomes and particle swarm for continuously varying type chromosomes. On to simulated annealing, which is special in that it is stochastic. However, it still tends to lock onto a local best. It does not do a global search. So the way we can picture this is we start off in some solution space, and it may not be this pretty, but for this example, I have it looking that pretty. So the black dot is our current design. So what we might do is produce some random changes to it. And we look at these and we figure out which one's the best. Well, that becomes the new point in our next iteration. Then we make some random changes to it, we figure out which one's best, and we move. Then we make some random changes around it, and we move. And if we keep doing this, we slowly walk toward the global best. But this tends to work better when the solution space is a little bit ugly looking and not smooth and continuous. If it really was smooth and continuous like this, I would say, hey, why don't you use a gradient descent or even a Newton method? So here's a block diagram of how a simulated annealing would work. We start, we randomize our current design, and so there's this thing that's a lot of times called temperature, because it's called simulated annealing, kind of like you anneal a material and you come away with a more pure crystal type pattern. So the temperature is really how much randomness you're going to introduce. So for low temperature simulated annealings, the randomness is very small, so we'll be taking very small steps through the solution space. Higher temperature, we take much larger steps. So very often what happens is we start off very hot and we cool. And so we take large steps at first, we start searching over a wider area, and then as we cool, we converge. So, but anyway, we randomize our design. And we search those, and we look, is it better than our current solution? If so, we replace the current solution. If not, we try that again, we randomize again. So as this iterates then, we'll start to slowly decrease the temperature to let it converge. So we're decreasing the amount of randomness that we're introducing. And finally, when some low temperature has been reached, or in other words, we're introducing so little randomness that we're essentially not doing anything, the algorithm is done. Some final notes. This really is modeled off true annealing, so the algorithm is inspired by that. And sort of like a gradient descent, this really is meant to fine-tune a design. This algorithm is not meant to search over the entire solution space. It's meant to focus on a local best, but it has a better ability to handle an ugly search for that local best. And I have seen this used for global optimizations. There are some tweaks we can make to this to make it search over the full global solution space, but really I think this is best applied to seeking out more of a local best, when that fitness function within the area of a local best is still kind of ugly. On to the last optimization we'll talk about, particle swarm optimization. This was inspired by nature, and they were looking for algorithms to emulate the movement of cooperative flocks or herds of animals. So the connection there is, hey, we got this flock of birds flying around for the best place to land. Maybe this could sort of be like a bunch of trial solutions, searching out the solution space to look for the best. So that's exactly what happens here. So here's the analogy between particle swarm optimization and our original optimization example, where we were looking to minimize diffraction efficiency. So our little trial solutions, these little circles with the vectors, are flying around much like this flock of birds, searching for the global best. And they cooperate, they have intelligence. So how does it work? Here's the simplest algorithm. There's lots of tweaks and hybrids of this, but here's the simplest. We initialize a swarm. So in other words, we pick the positions of all these particles, and we also pick their initial velocities. So what direction they're moving and how fast. Then we go through, we loop through all of these, and we do an electromagnetic analysis to calculate the merit functions. So maybe we're calculating a spectra, then we look at the spectra, maybe we get things like bandwidth and suppression and all this kind of stuff. We tie together into a single merit function or fitness function, and then based on that information, we update the swarm. And the swarm here is updated by changing their velocities. And when we change their velocities, then we change how they move, and they tend to search and fly around this solution space. And it's a very simple update, and we'll get more into what these individual terms are in the following slides. But it's a two-step process. We update their velocities. Given the new velocity, then it's easy to update the position. And we also, I'll describe all these parameters in following slides, but this constriction parameter here is something that we don't talk about, and I drop after this slide. But similar to the temperature in simulated annealing, we can put in that constriction parameter, which will tend to, as we make it smaller during the simulation, will tend to converge on a single solution. So we can almost make particle swarm behave like simulated annealing. So here's how we set up our optimization for particle swarm optimization. And in fact, all the optimizations are set up in a pretty similar way. We start off by identifying our different design parameters. What is a minimum list of variables that would completely describe our device design, that then we could simulate and figure out how good it works. And the challenge here is to describe as many possible different designs or many possible combinations as we can with as few parameters as possible. For example, if we have 100 things we want to control, we might not want to do that with 100 variables. Maybe we would try to do it with just 3 or 4. For example, maybe we're going to represent those 100 different design parameters with a polynomial. And so if we use a 4th order polynomial, we would have 4 coefficients, 4 numbers to vary, and then this polynomial would predict the other 100. So we're always playing tricks like that to describe as many designs as possible with as few parameters as possible. The more we can minimize the number of parameters, the faster we'll get the answer. The next thing we'll do is we'll initialize. We want to initialize all of the positions of the particles, and we want to distribute those as evenly as we can throughout the solution space, at least to start with. And each one of those positions corresponds to a specific design. Another thing in electromagnetics that's special to electromagnetics is a lot of times we can reduce the number of parameters using scalability. We would rarely want one of the parameters, for example, to be the period of a grating. We would always normalize that relative to the wavelength, and if we sweep wavelength and it's normalized, we don't need that. The grating period could be 0.5 or 1.25, and if we normalize it, it's always kind of the same thing. And then, so whatever answer we get in the end, we can just scale to whatever wavelength we actually do want. So think this way electromagnetically. How can we minimize the parameters? And then the last thing, and absolutely the biggest and most important one, is this merit function or fitness function. And I say here it may be the most critical consideration. I'll say in words it probably is the most critical consideration. I spend much more time playing around with my merit function than I do the actual algorithm itself. And the challenge here is quantifying how good a design is with a single number. This is challenging when there's multiple design constraints. And it's even more challenging when they have different importances and we have to suppress or enhance the different terms in our merit function. So here's the basic update algorithm. There's two steps. We update the velocity of a particle based on the new velocity. That's where all the intelligence of the algorithm comes in. So that's probably the hardest step. After that, we just update the positions based on the new velocity. And that's it. And so we really control the behavior of the particles through how we update the velocity. So here's the update equation for velocity and all the different terms. So we have the velocity of the kth particle at iteration I plus 1. So we're going to use information from the previous iteration to calculate the velocity for the new iteration. The first term is the inertia term. If, for example, the new velocity is always equal to the old velocity, we would say our particle has a lot of inertia. It's hard to knock off that track. So the bigger this W term, the more the inertia, the harder it will be to steer the particle. And the benefit of that is, if it does not turn abruptly, it will turn slowly and seek out more of the solution space. That's good, but it's also bad because it takes longer to do that. The next is our cognitive term. So this is the intelligence of the particle itself. And this R term introduces some randomness. C is our coefficient of the cognitive term, how smart it is, if you will. And the way this works is, we store, for the kth particle, we store the best place that that particular particle has visited. And so essentially this term is the tendency of the particle to fly toward the position where it has seen its best, its local best, if you will, or the best that specific particle has seen. We have a very similar term called the social term. However, this is not the tendency to fly to the best position that particle has seen, but in fact it's the tendency to fly towards the best that any of the particles have ever seen. So the global best, if you will. And there's lots of hybrids and changes and variations to this, but this is the basic particle swarm update. We have an inertia term, cognitive term, which is the tendency for a particle to revisit its best that it has found, and the social term, which is the tendency to fly toward the global best that the entire flock has found. And even more sophisticated, we can take these parameters, we can make them different for each particle, and we can make them change during the course of the optimization. So it can get pretty crazy. What I want to do now is try to visualize the effect of these different terms. So first we have the inertia term. Let's say we have small inertia, so this thing can turn very abruptly. So we have a design here that does a very abrupt turn. So we could say this will converge much faster. However, it searches less of the solution space. This, which has more inertia, does not turn as quickly because it tends to keep the same velocity. It searches out more of the solution space, but it takes more iterations to finally get to the best design. So if you have a relatively smooth solution space, the fast inertia term is probably best. If you have something really ugly, a large inertia term is probably best. On to the cognitive term. This is the tendency of a particle to revisit the best that that particle has seen. So if we have a small randomness and small cognitive term, well, it just seems to wander around sort of randomly. If we make the cognitive coefficient small but large r, it still wanders around, but even more randomly now. So like before, we're searching out more of the solution space. However, it also takes a lot longer to get to that best solution. If we have a large C and small r, then it tends to go straight to the local best. So it's acting, in this case, a little bit more like a gradient descent or maybe a simulated annealing. If both large and C, if both C and R is large, well, it tends to go straight toward this local best, but it also has this randomness built in. So it's always a trade-off of faster convergence on the best and searching out more of the solution space. The more of the solution space we search, the better guarantee we have of having the global best. The more direct, it's quicker, but we will probably get stuck in a local best type of trap. And then the social term, these pictures look the same way, but it's a tendency to get toward the global best instead of the best that that particle has seen. And so this is the sharing of information between the different particles in the swarm. And the final formula again, here it all is. Here's this constriction parameter, which I didn't talk a whole lot about, but this is sort of like the temperature in simulated annealing. I tend not to use it so much, but we can make particle swarm look a lot like simulated annealing. So imagine the beginning of an optimization. We're searching all over the place. We have maybe heavy inertia on the particles, so they're searching solution space. And as we iterate, we start to constrict these parameters, so the particles start flying more around what we think is the global best and fine-tuning it, and then it starts looking more like a simulated annealing. And in fact, maybe we can stop it at some point and finish it with a gradient descent. So that's the discussion on all the optimization algorithms. And I keep mentioning, I spend orders of magnitude more time on my merit function, fitness function, than I do on the actual optimization algorithm. So I want to take you through just one example merit function that we use a lot, that we call our rectangle algorithm, for lack of imagination of a better name, I guess. So suppose we want to design something that reflects over a very, very broad band. So what we're looking at then is we want this reflection curve to be really, really high over large a frequency range as possible. So we'll pick a design, we'll simulate it, and we get this ugly reflection spectrum. How do we analyze this to figure out how it's reflecting? Because we know we want bandwidth, we know we want strength of reflection. How do we tie all this together, and how do we determine that? So that's the goal of the algorithm. So when we're designing a merit function, here's what normally we might put in as ingredients: the bandwidth, reflection across the band. We talked a little about this before, but maybe also ease of fabrication. Maybe we wiggle our design parameters a little bit and we see how robust it is to deviations. If it's very sensitive, it's probably going to be difficult to make. Maybe we also want the simplest design. Are we also interested in some property of the transmission? Are we also interested in some kind of polarization response? What else could we possibly, maybe the size of the device? So for this example, we will restrict ourselves to bandwidth and performance. So by performance, we're talking about how good of a reflector it is, and bandwidth over what band it reflects. So think of our transmission response this way. And we have this dip in transmission, or high reflection, and what we'll do is we'll fit a rectangle to this. And the depth of the rectangle is a measure of the device's performance, how well it transmits or reflects. And we have the bandwidth. Over what bandwidth does it reflect or transmit? So in terms of the merit function, here's our steps. Step 0, which hopefully we've already done, so is barely a step. We decide on what our merit function is going to look like. And in this example, it's just bandwidth times the performance or reflectance, something like that. So really the first step for calculating the merit function is to simulate the device, calculate the reflection over some range of frequencies that we're interested in. Then once we have that, we loop through the spectrum and we look at each point in the spectra, and what we'll do is we'll seek left and we'll seek right to find the left and right edges of a rectangle. And then based on how deep that rectangle is and how wide it is, we can multiply those two things or calculate the area of that rectangle, and that's the merit function. And we do that for every point in the spectrum. And so our overall merit function for that device will be the area of the rectangle that was largest of all the rectangles that we experimented with. So this is really just a clever way of fitting the largest rectangle under this reflection curve. So let's look at that. So here's a movie of a reflection curve, and let's play it and I'll describe it as it's playing. So what we see is we pick a point and we seek left. We go to the next point, we seek left. It is also seeking right, but you don't see it since we're on a downward slope. Here you don't see the seeking left, but you do see the seeking right. So we pick a point, we seek left, we seek right, and we keep growing the rectangle until it stops. And once it stops, then we know the area of that rectangle. We do that really for every point in the spectra. This looks like it's taking a long time because we're playing a movie, but if we're not visualizing it numerically, this can happen very, very fast. But what you can see is this rectangle so far is the largest one, so that would be the preferred one. We would remember that. But we would keep going until we find a bigger one, and then we remember the bigger one. And in the end, as long as we've done this with finally enough spaced points, we've found what area under this curve supports the biggest rectangle. Here we actually see it going left and right. So we're taking large steps here. In reality, we would take as small of steps as the spectra will allow. This numerically is a very fast algorithm. We can do this essentially instantaneously, at least compared to the speed of the simulation. Remember, sometimes it could take a day or two to calculate this type of reflection spectrum, depending on how sophisticated the device is that we're modeling. So this calculation takes milliseconds, if that. Almost done. So anyway, that's the animation of this algorithm. We go one point at a time across our spectra. For every point, we seek left, we seek right. And we calculate the area of that rectangle. When we're seeking left, we keep going until we hit the curve again. When we seek right, we keep going until we hit the curve again. We calculate the area. So we calculate that rectangle associated with every point in the spectra, and the overall merit function is the area of the largest rectangle that we saw sweeping across this entire spectrum. Okay, let's play this movie. Now we're doing this much quicker. I'm not showing the seek left, seek right. I'm just showing as we're sweeping across this curve, the green rectangle is the current, or is the rectangle associated with the point we're looking at, and the red is the current best rectangle. That's the biggest rectangle that we've seen. So it's really the same thing that we saw on the previous slide. is we're not seeing the left and right seeking, we're just immediately seeing the rectangle after the seeking, and then the red is showing the best case. Let's play that one more time. So for every point in the spectrum, the green rectangle is showing the result after seeking left, seeking right, finding that rectangle. And then the red, we update every time the green rectangle is a bigger area than our previous best that we've seen. And so what we end up seeing is where that red rectangle is right now, that's the best under this strange reflection curve. It's the best with this merit function defined as the width times the height. If we change that definition, what is best changes. So let's suppress the importance of the width and promote the importance of the reflection. So we have a new merit function, and let's see where it finds the best. We're running the exact same algorithm, we just have a different merit function now. And notice, since it's preferring the height, we see it is preferring the regions where we have the highest reflection, because we've promoted the importance, if you will, of the reflection. So the height of the rectangle here is preferred. All right, let's go on to the next one. Here, we're suppressing the importance of height, and we're saying that the bandwidth, or the width of this, is the most important. Let's see what this finds as the global best. Notice that rectangle's way down because we're saying, hey, bandwidth is really, really important. And in fact, for this design, I don't think that changes. I think the red rectangle that it has right now is the best, because obviously it's very, very broadband. So it's really up to you as the engineer to say what parameter in your merit function is the most important and weighting it according to that. And this is very difficult. And again, I spend most of my time when I'm doing optimizations playing around with the merit function to actually find really what is the best solution to me. Okay, onward. So in the end, here's some real data that came out of some of our optimizations. So here we're plotting transmittance. So if we want something that's very reflective, we want the transmittance to be very low. So we're looking at it on a dB scale. And so we fit a rectangle, we calculate the area of this, and it ends up being 4.1428. Here's another design, which in fact has a bigger rectangle now with a merit function of 6.2044. So it would find this design as being better than this design. And notice I'm using a normalized wavelength. I almost always do that when I simulate, because we can always scale a design to whatever frequency or wavelength range we need. Well, that's it. I do want to make some final concluding remarks about optimization. The number one thing, and I've discussed this with many people, but there is no guarantee that your random optimization has converged onto a global best. The only way you could make such a conclusion is if you did a complete search or you know something about your solution space. Otherwise, you can't make that claim. But hopefully, we get a design that's good enough, and if we're engineers, not scientists, we can move on with life. So I tend to apply optimization this way. When we have continuously varying design variables, I tend to use a particle swarm optimization. When I have discrete design variables, I tend to use genetic algorithms. And for fine-tuning solutions, simulated annealing, gradient descent, those type of methods. And I've hinted briefly here and there that some hybrids work well. You could imagine taking a particle swarm, constricting the parameters over the course of the simulation so it starts in the end looking more like a simulated annealing, and then in the end jump to a gradient descent to fine-tune it. So that's optimization.